Welcome everybody to this SIMBa seminar. We have the pleasure to have here Josu, and researcher, and graduate student from the UV, which is going to talk about an illustrative example of class field theory, abelian extensions of QI via the cat cube. Yes.
Thank you very much for the introduction, and I promise to have a shorter title for the next talk. Okay, so let me begin this talk with the following classical result. Theorem. This is the Kronecker-Weber theorem. So this is telling us that if we take zeta n to be a primitive n root of unity, then the cyclotomic extensions, which are the fields that appear when adjoining to Q zeta n, then these are Galois. And furthermore, if we have any abelian extension of Q, then F is contained inside one of these cyclotomic fields. This is a very classical result, which I hope we are familiar with, because the rest of this talk will be to explain how to generalize this to when we change our base field from Q to Q of I. So let me just remark first that the goal of class field theory in the last century was to give analogous statements of this theorem when we change our base field Q to another number field F. And this was a successful theory, and in fact there are very general theorems. But what this theorem, this generalization misses is the very nice and explicit description of the abelian extensions in terms of the primitive n roots of unity. So before going any further, let me maybe record a little bit of how one goes about proving this theorem, right? So the trick here is that we consider this polynomial, and two things happen here, right? So first of all, the roots of this polynomial are all nth roots of unity. And furthermore, any nth root of unity can be written as a power of a primitive nth root of unity, right? Okay, I could set model set because they repeat, right? Okay, and then one has the following theorem, which comes almost for free, right? So when we adjoin Q of zeta n, then this is the splitting field of xn minus 1, so hence it is Galois. And the reason for this is all of these roots lying here because they are powers. So this is the splitting field and it is Galois. And furthermore, we have that this Galois group embeds here. So how does one go and prove this injection? Well, automorphisms in the Galois group are determined by where they map the primitive n root of unity. This has to go to another nth root of unity. So essentially, sigma of zeta n is theta n to some power k. And it is determined by the power k. A priori, this is in set model set, but because this sigma are invertible, then we can take a unit here. And this is essentially the theorem, right? This is this maps mapping sigma to k gives this injection, and well, okay. Now there are many more things that one has to prove to get to the full Kronecker-Weber theorem, right? First one has to prove equality here or isomorphism, and this is done by computing the minimal polynomials of the primitive n root of unity. Then one has to actually solve this statement, which is maybe the hard part of the Kronecker-Weber theorem. So okay, I'll omit all of this, and our goal will be to give a very similar result to this one, but for the case of Q5. So let me just take one step further, but not go again to still to Q5. Let me first build a bit our intuition with the following extension. So, for example, what about So the case of Q of I will be much closer in speed to this one. So let me talk a bit about this. So say we want to prove a similar result at the theorem like this for this extension, this sinusoidal extension, right? So how does one go about proving this? Well, so we need two ingredients, right? If we want to repeat this proof. So the first, we need some polynomials, right? With roots sinus 2 pi n over n times k, right? So we need some polynomials that contain all of these elements as its roots, and then we need to show that these roots can be expressed as polynomials in this one here, right? So something like this. And then notice that if we have this, then we are done, right? Because the second thing is telling us that the both in combined are telling us that this is the splitting field of the polynomials which have this root. And then a similar argument here with automorphisms will give us also an injection determining its Gaussian root. So the question now becomes, okay, which polynomials should we choose? And this may be a little harder to check, but I think that the second condition may be giving us some hint. And what we'll do is look at the addition formulas for the sinus and cosinus. So let me recall some trigonometry from high school. Which I hope you remember, otherwise it's here. So one starts with, notice that there are two formulas here. One starts with this simple formula, and we sum both equations to get cosinus of alpha plus beta equals 2 times cosinus alpha cosinus beta minus cosinus alpha. Okay, so what about this? Let's take alpha equals n times theta and beta just theta. And this is giving us something that looks like a recurrence formula to compute this cosinus. Right, so this suggests to take the following definition. So we define T0 of x to be 1, T1 of x to be x, and we use this formula to define Tn plus 1 of x, right? We define it as 2 times x, Tn of x, minus Tn minus 1 of x. And now, just by looking at these formulas, we have the following, which is that cosinus of n times theta equals p sub n cosinus of. Okay, so I know this is done for the cosinus, but well, cosinus of theta is sinus of theta minus pi halves. So there's like there's like a translation here, and we can take advantage of this formula to write sinus of n theta in terms of these polynomials. And I will skip the details here, but basically 1 minus 1 pops out, and we get this. Okay, so what about these polynomials? These polynomials are called the Chebyshev polynomials. If you are familiar with them, they appear in other contexts. And they are giving us the polynomials that we wanted, right? Because first of all, one can check by induction that the degree of these polynomials is n. And then by looking at this formula, it is clear that by plugging in values for theta equals 2 pi n times k, we get roots of these polynomials, right? And notice that we kill two birds at once, because this is also telling us how to write these elements in terms of sinus, right? Maybe by taking theta to be 2 pi over n, and here taking this n to be k, we get how to express these terms instead of sinus. So basically we are done. Now we have the polynomials, we repeat the same problem, the same process, and we get the following theory. So these extensions are Galois. So these are Galois. Sorry, these are the splitting fields of the T sub n. Hence Galois. And its Galois group embeds into the units model. Right? And maybe to further justify this claim, essentially it boils down to showing that the sinus is 2 pi periodic, right? So we have to show something like this. And this essentially follows because the sinus is 2 pi periodic. Okay, so very nice. So with this in mind, we are ready to jump into the case of Q5. And now we run into maybe a greater problem than before. Before we didn't know which polynomials to take. Now we don't have a function to begin with, right? So this will be when the lemniscatic curve enters the picture. Okay, so in order to construct a function analogous to the sinus for Q of I, we consider the lemniscate. So let me introduce the lemniscate. It is the following figure of an eye. It's also known as Bernoulli lemniscate, and it has one definition like as the geometric set of points, right? So here we have one focus A and one focus B, and the lemniscate is the set of points such that we take the distance to this foci, so D1 and D2, and we are asking for the product of these distances to be constant, right? I think like if one takes the sum, I think one gets the ellipses. By taking the product, we get the lemniscate, which is a closed curve as well. Very nice. And in fact, we are going to take this lemniscate for the following constant, right? So here we have a -1. This will be -1 over the square root of 2. I'll explain why we care about this. So the reason we care about this is that this figure here will play the same role the circle does for Q in the theory of extensions of Q pi. So maybe let me draw the circle in question here. So okay. Now I'll start to explain how to construct our function. So maybe let's forget a second about the lemniscate and let's see how one construct the sinus from the circle, right? So maybe it is more natural by looking at the geometric picture to define the arc sinus, right? We can define this as the arc sinus of R in terms of this integral. Right? This is because we have some Cartesian equations for the circle, and we can use them to compute the arc length of the circle, and we can define this nice formula. Okay, we can do the same for the lemniscate. Let me just write the equation. So here we have something like this. Okay, whatever it is, and we can similarly define a function that measures arc length. It's going to be here. Okay, so here now we have although the function looks maybe the Cartesian equation looks much more uglier, the formula is still very similar. And how do we keep going on? Well, where is this function defined? Well, this function maps an element in -1, 1 to -pi halves. So what will be the analogous for pi here? Well, here the length of this thing is the 2 times the integral 0 to 1. Okay, so maybe yes. Okay, I'll write it. And this is 2 pi, right? No, this is pi. Maybe okay. Maybe I'm messing out something. Just 2 times. No, this is 2 pi. I think something like this. Maybe I don't. Or maybe this is. Maybe we need a 4 here. I'm not sure. Maybe I'm making some mistakes. Just in case I'm making some mistake. But in any case, we do a similar thing here, right? What is the length of the full thing? Well, we take the arc, this arc, and multiply it 4 times, right? So this is 4 times this integral. And we use this as a definition to define this omega bar. This omega bar will play the same role as pi does for the abelian extensions. And this function here maps from -1, 1 to minus omega bar halves. Okay, very nice. So now we have our function, but it is the inverse of the function we are looking for. So we have more work to do, right? So how do we find the sinus? Okay, now this is easy. We can define it as the inverse of the arcsinus. Maybe a definition. So we will define the lemniscatic sinus in the similar fashion as the inverse of the lemniscatic arcsinus. And the inverse of the adelic function. Okay, very nice. But this function is only defined in a very small interval of time. So we actually want a holomorphic function on C, so we have to extend this to C. So how do we do this? Well, we just look at the sinus and copy. This is the game we are playing, right? So how these functions look something like this. Right? And we extend it first by symmetry to 3 pi halves, and then by periodicity to the whole. And we do the same thing here. And here, this is more than an analogy. If one actually computes how this function looks like in this small interval, then it looks very similar to the sinus function. It is essentially the same, but maybe more. Okay, this actually goes through 0. Okay, I think I've done the wrong problem. Okay. So essentially, we have now we have our function defined for the real numbers. And one can go further and extend this to the complex numbers. I won't go into details, but basically one can use Taylor expansion, for example, and use this to define a holomorphic function. So I guess that there might be one question in your heads now, and why do we care about this, right? Because it looks like one could have taken any other closed curve in the plane and play this game of defining the function that measures arc length, then consider its inverse, extend it to R in a similar manner as we did for the sinus, and we will have again a complex function and all of that. But I will convince you that this function is actually interesting and it has some properties that not only resemble the sinus, but are very, very special. So let me state some facts about this function. So facts. So first of all, we can write the derivative of the lemniscatic sinus as the square root of 1 minus SL to the 4. Okay, this looks like nonsense, but maybe if I write, say, we define the cosinus lemniscatic, I don't know how to say this, the lemniscatic cosinus as the derivative, then this is telling us that the cosinus squared plus sinus to the 4 equals 1, which is not so far from the usual formula for the sinus. Okay, then we also have this. The second derivative is minus 2 times SL cubed, which kind of resembles the formula for the sinus. And which is more important, we also have the following addition formulas for the lemniscatic sinus. Now this is rare, right? Like if one does the process for any other closed curve, there is no reason why we should have a formula like this. Now this is very similar to the formula we are used to, but it has some annoying denominator. And this is the formula that we are looking for, right? Because now that we have this, we are basically done. We can again play this game of taking addition of angles and defining formulas by recurrence relations. And then this will be the right polynomials, right? The roots will be the numbers we're interested in, and this will give us splitting fields and Galois and all of that. So let me state how this goes, but there's even something more interesting here, but because there's another property of this function, which is the following. And here one may argue that this is even a more interesting function than the regular sinus, because this means that it is double periodic. This is very interesting. And one of the reasons, when I was considering the case of sinus, one may wonder, does this give us abelian extensions of Q, or does this have an analogous statement for the Kronecker-Weber? And of course it is going to fail because these are all totally real extensions, right? So there's no hope of getting all abelian extensions. And this is telling us that, okay, maybe here we have more hope, right? There is hope of getting complex extensions, so maybe we can get some. And this is telling us again that we can apply these formulas and not only get recurrence formulas for n, but even for greater for greater integers, we will have recurrence formula for Gaussian integers. So if we take beta to be a Gaussian integer, okay, I forgot about one part, but this formula follows when n is odd. This is important. There has to be some oddness condition here, right? Then we have the following. Okay, so these are our. Okay, so I skip the recurrence formulas and I reach the polynomials. These are the polynomials which satisfy some recurrence formula. And this looks very much the same as the one for the Chebyshev polynomials, so we can take advantage of this to construct our abelian extensions. So okay. Now, because the addition formula is a little bit uglier and we have to work with Gaussian integers instead of regular integers, things get a little bit more tedious and there are more subtleties, but essentially the following theorem.
What do you mean by odd in this proposition?
Yes.
Beta is
So we can write beta as A plus Bi, right? And we say that this is odd. If A and B are, okay, sorry, maybe even, never mind. So we say they are odd if they are not congruent. This is the oddness condition. Yes. So okay. So one of the things that is annoying us is that these are rational functions. So in fact, one actually has to write R beta as a quotient, and now these functions like these have algebraic integer coefficients. This is interesting, right? Because if we want to have algebraic integers, as in the case of Q, and now this is the function that we are looking at, d beta x t. This is the function whose roots are all of the form, say. So its roots are of the form something like this, maybe. And this is also telling us how to write. So we can write this in terms of here we have to multiply by something, right? It is the one we are choosing. So these are going to be our algebraic integers, and these are going to give us the abelian extensions. So this is the theorem. So the extensions that happen when we are joining these points in the length scale. Notice that we have to adjoin I now because these are polynomials with Gaussian integer coefficients. This is the splitting field. Polynomials. And furthermore, the Gauss group injects into here. Okay, so many remarks. Let me explain a little bit this theorem. So first of all, why do we have two omega bar here instead of it's because here the roots, sorry, this has to be some like a priori we'll have something like this, right? Like some omega bar over beta by looking at the recurrence formulas and using periodicity. But well, one can actually restrict to the case that these all roots can be expressed in terms when this omega here is odd, and then well, essentially multiplying by 2 here doesn't lose any roots, so we take this. And the reason we want to take this is that by periodicity again, then we'll have that 2 of these roots are equal if and only if alpha and omega are congruent modulo beta. Right, this is by periodicity, and this is why we have the injection in this group. And this theorem is so these extensions are the right ones. One can actually prove isomorphism here in all cases, and one can actually show again that any abelian extension of Q of I is contained in one of these extensions. And this gives us a true analog of the Kronecker-Weber theorem. And maybe some concluding remarks. So why did I call this an illustrative example of classical theory? So maybe what is going on, right? So these lemniscatic sinus functions, these are called elliptic functions, which are double periodic meromorphic functions. I'll write this in a minute. And the fact that it has addition formulas is telling us something very interesting. So an elliptic function this is a double periodic meromorphic function on C. So SL is an elliptic function. And what is interesting about these functions is that because they have two periods, right? We can think about the complex plane and think about the two periods of this function. Then these functions are determined in a very small lattice. And only zeros and poles here completely determine these functions. So what we have is that these functions are actually defined in a quotient like this. And now if you are familiar with complex geometry, then you'll recognize that this is an elliptic curve. And in fact, elliptic functions parameterize elliptic curves. So we'll have something like this. Let me write it like this. We'll have something like this for the lemniscatic sinus. In fact, let me just tell you, just for interest, that the equation for the elliptic curve that is attached to the lemniscatic sinus is the following. And the torsion points of this elliptic curve correspond to the elements that we are adjoining to our extension, which are furthermore the division points on the lemniscape. So what is happening here? So because this is a homomorphism, what happens is that zeta plus zeta prime gets mapped to this thing here, right? Okay. And so if we consider here the same elements, then this is giving us like how does this is a homomorphism. So these are this multiplication by n here. What I'm trying to say is that multiplication by n here corresponds to multiplication by n here, right? So the fact that we have extra addition formulas is giving us extra endomorphisms for our elliptic curve. And what is going on here is that the elliptic curve attached to the lemniscatic sinus has complex multiplication. And now we enter a very powerful and very general theory, which maybe I can recall the following theorem. So theorem, if K is a quadratic imaginary field, and we take an elliptic curve defined over K with complex multiplication, so it has more endomorphisms than just multiplication by n. Then we have a theorem that characterizes all abelian extensions of Q. And these are determined by adjoining the J invariant of A and the torsion points of the elliptic curve. Okay, there's one little thing here. Okay, so there's a little remark here. Does this cover all cases? Well, no. Notice that we can these extensions when we just consider K here. These are Galois, but they need not be abelian. So we actually need to add this J invariant, and if this J invariant doesn't lie in our field, then we don't have the abelian extensions of K. So maybe here K of J, right? And well, this theory has been vastly generalized by Taniyama, Shimura, and many others. And one can replace here K by the quadratic imaginary extension of a totally real field, and E by an abelian variety, it's complex multiplication. And yes, we have very powerful theorems even for explicitly determined abelian extensions of Q, but maybe what I would like to end my talk with is that although class field theory was proven and it was a major success of the last century, there are many phenomena that we still don't understand, that we can hope for better explanations. And in particular, for example, this game of finding analogs of Kronecker-Weber's theory, finding explicit constructions for the abelian extensions of number fields is not solved yet. So that is all, and I hope you enjoyed the talk, and thanks for your attention.
Any question to the speaker?
How special is the lemniscatic curve? Because it's a variable elliptic function, I agree with you that you have an elliptic curve and you can carry out this theorem. But can you go the other way? So you had the lemniscatic function, you got some doubly periodic metamorphic function. If I give you one of these functions, can you give you some curve or geometric object? That's not elliptic.
Maybe yes. So maybe to give an idea. So in general, if you consider an elliptic function, it will not have addition formulas. So it corresponds that in general, if you take an elliptic curve, it will not have complex multiplication. And then about constructing a very nice geometric, I think that it's even nicer because so there's many more things that one can say about the circle and the lemniscate. So these points are actually these numbers. These are actually like the torsion points of this figure, right? So the division points, sorry. So they break this into arcos of equal length and so. And well, I don't think that the converse is easy to give. Like I know, for example, Gauss and many others already knew about the addition formulas. So I think that the study of this figure and the lemniscatic sinus and stuff came first before relating it to an elliptic curve. And I think that in general, yeah, hard problem. Yes, I don't know of any other.
Just by curiosity, do you know any other example relating arc length of figures of curves and maybe elliptic curves or modular apart from the lemniscate?
Yeah, so actually I don't know more. There may be more, yes, but I haven't. I don't. Yes, yes. As I was mentioning to Enrique, this was known to Gauss and other people. So maybe like in the case of the lemniscate, at least the study of this figure and the function came way before first relating to an elliptic.